Hello, this is part 2 of my project to improve parallel port performance and SD card performance for my 6502 breadboard computer, and things are going remarkably well. It is already very much faster than it was to begin with. So if you want to see how it got this way, keep watching, and I'll show you the second batch of experiments. If you haven't seen part 1 yet, I suggest you go back there. If you want to see the source code, it's on GitHub. There will be links to all of that stuff down in the description. So keep watching. This project was a lot of fun. So first, since I finished recording the last video, there have been a few interesting developments in the Project 65 SD card performance story. So the last thing I had done was add this SD read routine, which is a buffered read routine that is optimized for the parallel port protocol between the 6522 and the Arduino. And that gave us a nice performance boost. And I wanted to do a write routine too, but I had the problem that I was out of room in the dispatch tables that are used by the device driver system in my kernel. So I had to go back and refactor a few things, move some things around to make room. Since then, I have been able to add the write routine that matches the read routine, does pretty much exactly the same thing, sends a 3-byte command with a command number followed by a 2-byte count of the number of bytes to write, and then just goes into a loop of sending, however many bytes. One slight change from the logic of the read routine is at the end I return a 2-byte status code that this routine reads from the Arduino. And this is a 16-bit integer, and if it's positive, it's the number of bytes that were actually written to the SD card. And if it's negative, then it's an error code that we go ahead and treat the same as we do all the other error codes in the system. And with that in place, I've been able to update my scorecard once again. So this time we're getting 1.14 seconds. Now when I updated the scorecard earlier today, down at the bottom here, I was getting 1.16 seconds for the write test. And I have noticed from time to time that couple of tenths of a second variation, just going from checking one evening to checking the next day to checking the following evening and sort of thing. And I wonder if there could be something where some of the timing or the behavior of the SD card might be a little bit temperature sensitive or something. I don't really know for sure. But there is that little bit of inconsistency. Within a given run, it'll be very consistent. If I do this again, I'll probably get 1.14 or maybe 1.15. But I was definitely seeing those 1.16, 1.17 second results a little bit earlier. So that's something to keep in mind. But most of our algorithmic changes have made much larger changes to the overall performance numbers than that little bit of noise that seems to be entering in from somewhere. Still, something we should probably keep in mind and watch out for. There's something else I noticed, not when I was recording the last video, but when I was going back and editing it. And the easiest way to demonstrate it is to show you the logic analyzer results. And it had to do with the overall time that the operation was taking. And here, with this set of results, we're zoomed out so that from here to here is 4 seconds. And this is the section where we are loading the program, the disk speed program. And this is the section where we're writing our 10 kilobyte test file. But what is this section here? What is this 1.31 seconds? And honestly, this is the improved version. When I was first looking at this was 3.4 something seconds. So what was going on? What was the program doing between when it finished loading and when it started running and when it actually started writing the channel? Well, I found out, and it's all due to just a couple of lines of code in the C program. So here's the write test routine, and it's pretty straightforward. We allocate a 10 kilobyte buffer, we fill it with some more or less regular data, and then we write it as just a single write command, the entire 10 kilobyte buffer. But the place where all of that time is being spent during the initialization of the program is just in this for loop. And initially I was doing it with this line here that is commented out, just taking the loop variable, modding it with 256 so that I was filling the buffer with just a repeating pattern of the characters from 0 to 255. But like I say, that was taking 3.46 seconds. I did a little change. Instead of using the mod, I'm just doing the cast from an integer to a character. So basically just truncating off that top byte, just taking the lower byte of the 16-bit number. So that does exactly the same thing. It fills the buffer with the exact same data, but it only takes 1.31 seconds. And I also played a bit with the optimization settings for CC65 since I haven't really used those at all and am not familiar with how they impact performance very much. But in this particular case, in this one tiny example, they made no difference whatsoever. So that's an interesting example how when you're using CC65 that performance can be affected by what seem like very minor things, especially if you're used to programming on systems that are modern and have modern amounts of horsepower. I wouldn't think twice about doing this sort of thing. I guess it is kind of redundant, but I wouldn't really think twice about doing that on a PC. But here it makes a huge difference. So I want to go back to the logic analyzer for a bit. For one thing, because the logic analyzer is cool, but also because I've added a couple of lines that I didn't have when I was doing the previous video, and I wanted to explain what they were before we go any further. So the top two are what we had before. They're the CA2 and CA1 signal lines between the 6522 and the Arduino, and that's how the communication on the parallel port is being synchronized between both sides. And in these sections, it looks like just a solid bar here, just because we're zoomed out so far and a lot of communication is taking place within these larger sections. Now this red line here, this is new. This is hooked up to the IRQ input of the 6502 processor on the P65 computer. So this will show any time that the 6502 needs to service an interrupt. And there are two sources of interrupts in the system right now. The first one, and it's almost all of what we see here, is the real-time clock timer on the 6522. I've got that configured to send an interrupt 100 times every second, and that's what the system uses for most of its timing measurements of any sort, but including our performance timing of the disk speed program. And that's what the vast majority of these lines here are, though there's a little bit of aliasing going on because we're zoomed so far out. The other source of interrupts is the serial port driver, which generates interrupts when a character is being received or when its buffers become too full or empty. And that's what you can see happening right here at the end. This is where the program is just finishing and it's writing out the test results. So it's generating a few characters of output right here. This final orange line here is hooked up to the SPI bus, the connection between the Arduino and the SD card itself. Specifically, it's hooked up to the clock line. So anytime there's communication, the Arduino sending data to the SD card or vice versa, or both simultaneously, because you can do that in SPI, it's full duplex, there will be activity in this orange line. And that kind of confirms some of the things I suspected earlier. So right at the front here, as it's trying to open the file, it has to load a few blocks to look up directory entries, find out if the file exists, find out where it's located on disk. Then each of these spikes here corresponds to reading in 512 bytes of data off of the SD card. And the spaces in between are where those 512 bytes of data are being sent across the parallel port from the Arduino to the 6522 and the 6502 processor. Over here on the right side, there's a little bit more upfront information because we're overwriting an existing file, so it probably has to deallocate some previous blocks or something like that. I don't know specifically what's happening. But then we go back into the same sort of pattern, only this time each of these spikes is writing 512 bytes of data. And in fact, we can zoom in really, 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 really far to the point where we can see the individual bits of data being sent through the serial interface. So each of these sections here, this set of 8 spikes in the line, is 1 byte of data being sent across the SPI bus. And we can see that this clock is running at 4 megahertz. So that's less than the actual clock speed of the Arduino, which is 16 megahertz, but it's still very fast. It's being done with some hardware assistance. So it's not being done all in software like our parallel port interface is. And that's why it is so much faster. Or at least it's usually so much faster. Because I also had, from a couple of days ago, this very interesting trace, where the SPI part of the write operation was taking a lot longer. So the background on what's happening here is that I mentioned that I had to do some refactoring in order to add the customized write operation. And I took the time to do some more refactoring and rearranging while I was at it. And because I had changed a bunch of things, I wanted to test it all out very thoroughly to make sure it was all still working, there weren't any regressions or anything like that. And one thing I did during that testing was I ended up cleaning up a bunch of folders on the SD card. I deleted a bunch of very large sort of nested hierarchies of folders that I had created when I was testing different kinds of recursive moves and copies and things like that. And for some reason, after I had done those operations, all of a sudden my timing results for the write test were taking much longer. The read test was basically unaffected, but the write test was all of a sudden behaving like this, where the parallel port communication was still taking the same amount of time, but the SPI communication between the Arduino and the SD card was taking much, much longer. And that meant that the overall communication was taking much, much longer too. It went from 1.14 or 1.16 seconds to almost 2 seconds. And it's not just that the SPI bus is running more slowly either. If I go to this trace that was just after I fixed the problem, and if we look at the timing on one of these spikes, so when things are working correctly, quote-unquote correctly, it takes about 3 milliseconds to send 512 bytes of data to the SD card. And in the course of that, I think these n rising and n falling are the counts of the number of rising and falling edges inside this block that I was timing. So 6,000 rising edges, which means basically 6,000 bits, that's like 700 some bytes, being transmitted across the SPI bus during that time. But if we go back to the one where things were acting weird, and look at one of these spikes and the timings, well, first off, we see it took 50 milliseconds, but we also see that there were 84,000 rising edges and falling edges. So that means 84,000 bits, more than 10 kilobytes of data being sent across in each one of these little operations. What is going on here? I still don't know for sure what is happening. I've looked a little bit at the code for the SD library and the SD FAT library and how they do the SPI communication to the SD card, but I don't understand it fully because there's a lot to it. I did confirm to myself that internally it was using this 512 byte buffer, and I can see where it's doing some write and synchronization type of operations. It does look like when it's writing a block of data to the SD card that it does have to do some sort of query where it's waiting for the SD card to report that the write has completed. So maybe something like that is happening. It's writing the data and then it's spending a long, long time waiting for the SD card to tell it that that communication has finished, that the write has finally made it onto the SD card. But I don't know for certain. And I don't really want to get sidetracked too much into digging into the SD card library. And the whole point of using the Arduino and the SD card library was that I wouldn't have to go digging into it too much and I could work on other things. But still, I did say that I had fixed this problem, or at least I have resolved this problem for the moment. And how did I do that? Well, I caused it, as near as I can tell, by deleting a bunch of very large directory structures. So maybe that changed where on the SD card this 10 kilobyte test file is being written to. And maybe something about that location now takes more time to write to or something. And I don't know if that could be due to the file system structure or because of the wear on the SD card or something like that. But just on a hunch, I decided to try to fix it by creating a couple more large directory tree structures, just replacing the ones that had existed before. And surprisingly, that worked. I did that, and I went from getting this kind of timing back to getting, well, I'm zoomed out here, back to getting this kind of timing, which is what I was seeing before, and back to getting this one that I just recorded just now. It frustrates me that I don't know exactly what's going on, but for the time being, it seems to be stable and acting like it was before. And now I'm not certain what the best course of action here is for this, but I think for the time being, I'm going to set this little question aside for a while, because you can't really investigate two things at the same time. You'll just trip over your own feet and not understand your own answers. So as long as these timings are acting consistently and consistently good now, I'm just going to go with that and focus on the parallel port communications like I was originally intending to. And should this problem pop up again in the future, maybe we'll investigate it some more then. And if anyone out there has any thoughts on why this might be happening and wants to add some comments about that, that would be highly appreciated. Okay, so the next place I wanted to look for ways to speed up this parallel port connection was the disk controller code on the Arduino side. And I thought specifically this write byte routine would be a good place to start. Now, we've seen before from the logic analyzer that the 6502 side of the parallel port tends to spend more time waiting for the Arduino side. And the reason for that is that here on the Arduino side, I'm using the regular Arduino IDE and its APIs. And that means whereas on the 6502 side, when I want to set a value on the parallel port, I can do that with just a couple of machine language instructions. Here I'm calling functions from the IDE for each and every pin that I want to change. So here, where I'm writing a byte to the parallel port from the Arduino, I have to set all of the data pins to be outputs, and then I have to set their individual data values. And then I have to wait for the 6502 to read the data that we sent, and then we have to set all of these pins back to being inputs. So there's a lot of these individual functions to access these individual pins, and from what I've heard, these functions are not overly fast. That's not really the priority for them. They're meant to be easy to use and safe to use and to support a bunch of different related microcontrollers. So raw speed isn't the number one priority for them. But that also means that if we find out how to talk to these ports directly, we can probably do something quite a bit faster. So I went online and I found this page in the Arduino documentation that talks about the raw registers that control the data ports for the individual pins. And it turns out that in an Atmega 328P like what I'm using, there are 3 ports B, C, and D. I don't know what happened to port A, but here we are. And currently the way I've got things wired up, I'm using pins in port B and port D. Port C is the analog input pins, and we could use those if we wanted to. We could use those as regular digital pins from what I understand. But I don't have those connected just now. Port D has 8 pins to it. Port B has 6. Port B is also being shared. We're using a couple of pins from it for the parallel port, and we're using 4 pins of it to run the SPI connection to the actual SD card. So that's an example of why those functions like pin mode have to be so careful not to change data, because you'll have different functions doing different things with different pins, and you want to make sure you don't overwrite something that you didn't intend to overwrite. So that's something we'll need to watch out for. And to make things a little bit trickier, I'm using kind of a weird assortment of pins here. These are the numbers for the Arduino digital pin numbers. So I'm using pins 0 and 2 for the control lines. And for the data lines, I'm using pin 1 and then pins 3 through 9. It would be nice if I were using a contiguous group of pins for the data lines. The reason I'm not is that currently I've got an interrupt set up to check for changes on control line CA2, so to check when the 6502 changes its control line. And it turns out that in order to trigger an interrupt on a pin changing, you have to use pins 2 or 3. Though also, I'm not sure with my current version of the protocol that I really need to be using an interrupt for that at all. So we might experiment with getting rid of that. But I'm not going to do that right away. I think the first thing I want to do is get rid of those function calls that I'm using to talk to the pins and replace them with some direct port manipulation. And yeah, the fact that we're doing some weird discontiguous pin numbers here means that the math of that is going to be a little bit trickier. There'll be some bit manipulation. It'll be fine. We'll figure it out. We just need to run, and I'm going to write this down so that I can have it handy. Just so I remember which port is which. As we go back over here to the IDE and figure out exactly how we're going to do this. Now, the ports work basically the same way that the ports on the 6522 on the other side of the parallel port work. There's a data direction register and there's a data register. I think what we're going to do first is we're just going to replace these pin mode calls here and here. I think that'll be the simplest thing to do because these are just going to be constant values. I don't have to worry about the individual data values that we're going to write here. And we'll just see if that makes any difference to the performance. If it doesn't, then we know we're wasting our time and we can go try to do something else. But if this looks promising, then we can figure out this slightly more complicated bit of bit manipulation here. So here, this is where we're writing a byte to the port. So we need to change from input mode to output mode for all of the pins that we're using. We also need to make sure that we don't change any of the pins that are being used for the SPI communication to the SD card. And we need to make sure that we're not messing with CA1 and CA2. So let's see, DDRB, that's the data direction register for the port B, needs to be, we'll just write as a binary value. Pins 7, 6, 5, 4, and 3 are all going to be set to outputs. Pin 2 is going to be an input, and then pins 1 and 0 are going to be outputs. And we're using that whole port so we can just set that value directly. Oh, wait, that's not B, that's D. Port D is bits 0 through 7, sorry. Then DDRB. DDRB, we need to set pins 8 and 9, so that's the two lowest bits in port B. We need to set those high, but we need to not change anything else because that would interfere with the SPI stuff. So let's see, I guess what we actually want to do is a bitwise OR. I think that's right, and then we can comment out the pin mode calls. And then down here at the bottom, we need to do mostly the opposite. CA2 is still an input. Data bus 0 becomes an input. Pin 0, which is CA1, remains an output. And here we just need to clear the lowest 2 bytes. So we need to 600, and we'll do a bitwise AND into that. Okay, it'll be interesting to see if I got this right at all. So when I was recording the previous video, I didn't get any really good footage of my process for updating the Arduino that's actually doing the communication with the SD card. So I thought we would remedy that today. So first off, I have two of these Atmega 328Ps. These are the microcontrollers that run the Arduino Uno. So I take the spare one, I stick it in an Uno board. Not all the way, just enough to make contact because I'm going to be taking it out in a moment anyway. Fumble around on the floor for a USB cable. Hit the upload button on the Arduino IDE and you should be able to see the lights flashing as it is programmed. Take that out, use the chip puller. This is very awkward to get the camera angles in. Voila. Now here's the part that I've forgotten a couple of times. Turn off the power to the Project 65 board before we use the chip puller to pull out this 328. You don't really need the chip pullers for this, but it's easier to get in there because I've got all these extra wires here going to the logic analyzer right now. Put the new chip in, being careful to face it in the right direction. Push that firmly in. Turn the power back on, hit the reset, and we should be good to go. Okay, I've got the chip swapped. I don't need to make any changes on the 6502 side. Now, let's go back over here and look at the scorecard. So, this will only affect the speed of the read test because this affects what's happening when we're writing bytes from the Arduino to the 6502. So we've been at 1.78 seconds for that before. And assuming this actually works, let's see what we get now. 1.09 seconds. Okay, that's actually kind of impressive. I was expecting that we would get something that would match the speed of the write. So about 1.16 seconds, because the write doesn't have to do any of that pin mode stuff at all. So 1.09 seconds is a very nice improvement. Let's try that again, just to see how consistent it is. Okay. And just to see if write is still doing what we expect it to. So that's really encouraging to me. All right, let's think about this some more. This is more complicated. I want to fix the digital writes in, I suppose this will be data D and data B. Okay, we know that CA1 and CA2 should both be low here. I don't think writing to CA2 is going to make any difference because it's set as an input. But we have the least significant byte or least significant bit of data is going to be off all by itself. So let's see. And we're going to do a bitwise OR of that with the other 5 bits of data that are going to be on this port, but those are going to be shifted by 2 spaces, I think. And then data B, we need to set the values for the 2 least significant bits with the 2 highest significant bits of our data, but we need to do that without changing any of the other bits on the port. Let's see. Does that look right? I'd be very surprised if I got that right on the first try. What the heck, we'll try it and then we'll debug it. If we got things wrong, loading programs will not work. So we'll know right away. Updating the Arduino. Did I get my variable names wrong? Oh, port, not data. Okay. Ever have days where you just can't type correctly? There we go. Okay, chips are swapped, so we'll go back to Terra term here. Let's just see if we've completely broken things. I would say that we have completely broken things. Let's reset. One way to test that, I can download a clean copy of the disk speed utility and run it, and it'll tell me if it's reading something. If it's able to finish reading data at all, it might not. Let's see what happens. No, that is not working at all. Okay. We're just going to need to take a look at this and think about this until we get the math right. I am assuming these registers are only 8 bits wide. If they're 16 bits wide, that would do some weird things, maybe with the values that I'm writing. But that seems unlikely. Oh, I think I see what it is. Bit 1 here isn't in the 0th position in the register. It should be in the 1st position. We'll try this. It can be hard to concentrate when you're filming something, and I just want to mention that I just took the Arduino out of the breadboard while the whole system was powered on. I'm sure it'll be fine. I got the other one swapped in, and we'll reboot the system and try again. That's a good sign. And for the disk speed, we get 0.69 seconds. Oh, okay, let's think about that, because our original time for reading was 3.52 seconds. Oops. So we're 5.1 times faster than we were before. So like a 410% speed up. I'm really happy about that. I'm going to do that one more time. Even better. I'm going to go offline and do the same change in read byte, and then take a few data points, and we'll try the next experiment. Okay, so I've made the equivalent change in read byte, where we're building up our result value out of the bits and pieces of these two registers here. Now, I was actually going to make kind of a smarmy comment about how it's so much easier to do this kind of bit manipulation when you're not recording yourself, but actually getting this one right took me 3 tries instead of 2. And that was because I forgot that for the Arduino data registers, there's actually a different register for reading and writing. So when we write to the port, we use like port D and port B like we do down here. When we read from it, we use pin D and pin B. I've also gone through in both the read byte and write byte and switched all of the control lines from using digital read and digital write to looking at the bits in the port directly. Here we're checking if CA2 goes low. Here we're setting CA1 high, and here we're setting CA1 low. And doing all that has had a pretty nice effect. And you can see here I recorded several trial runs, and yeah, we've cut off even another 1/10 of a second from the read time just by switching over the control lines. So I'm really happy with how that has turned out so far. That made a huge improvement. And I'm not sure how many more things there are that I can come up with that are going to actually make a meaningful improvement, but I have 1 or 2 more ideas. I'm out of time for this evening, but maybe tomorrow I'll add a little bit more to the video, and we'll see what happens. So last night, instead of editing the video I had recorded like I intended to, I got an idea and I wrote some more code, and it seems to have worked out pretty well. So let's go through that real quick. So we've been looking at read byte and write byte, which are the raw functions to put things on the wire, but this latest thing I've worked on is for the code that calls those functions, and it's a little further down here in file RW, which is the handler for a file that has been opened for reading and or writing. And let's go down to read. Here you can see what's going on. So the previous version of this code just used this loop, which we'll call the non-buffered I/O version. And that means that when the 6502 sent a read request to the Arduino, it would eventually go into this loop, and for each character that it needed to send, it would make a call into the SD library's read to read 1 character at a time. And initially I thought that was pretty reasonable. I could buffer things in this class also, but it seemed like that would be redundant because the SD card library is also doing some buffering. But I ended up looking at how this read was defined a little bit as I was going through the source code, and I noticed that it actually does have a fair amount of overhead. So I thought it might be a worthwhile try to see what would happen if we called it less frequently. And that's what caused me to write this second version. Same basic loop, but instead of calling the SD card library read function for each character, we're calling this next car routine, which is just down here a little bit. And what this is doing is that it's a 32-byte buffer. So every 32 characters will make an SD card read operation. But most of the time we'll just return a character from the buffer. And sort of the same thing with writing. We'll fill up a 32-byte buffer and then write it out all in one go. So will that actually make any significant difference in our performance? Well, let's take a look. Here's where we have been last time with our work on the control lines. And now with the buffered I/O in place, our write time goes to 0.38 seconds. So that's a pretty significant improvement. And the read time also drops, although not quite as much. It's interesting that in this particular run they both gave me the exact same time. That's not usually the case. Now, the neat thing here is that if you go back up to the top here, especially for the read time, we're getting very close to a 10 times performance improvement. It sure would be nice to cross that line. I would be satisfied at that point, for sure. The write speed I still don't care about quite as much as the read speed, but it's also much better than it used to be. Now, there are some complications with this buffering, so I was a little hesitant to do it. One thing is that, for example, in implementing seek, I have to be very, very careful to flush the buffers when we do a seek operation. And similarly, when we do a file close, if the file has stuff still in the write buffer, that needs to be flushed out. So there is some complication there. The real complicated situation would be if a file was open for both reading and writing at the same time, which the interface does allow. And I decided I didn't want to really try to deal with that. It's not something I particularly use very often, and the semantics of it, I think, are fairly complicated. So that's why I still have this if statement in here and both versions of the loop. So if the file is read only or write only, we'll use the buffered IO. If it's open for reading and writing simultaneously, I'm not going to use the buffered IO inside of my classes. We'll just hope that the SD card library is doing the right thing. And that's a limitation that I don't think is going to bother me at all. Now there is one other little experiment that I wanted to try here on the Arduino side, and it is going back to those read byte and write byte routines. And it has to do with this interrupt funny business right here. So I think I mentioned before that earlier versions of this code had used pulses on the CA1 and CA2 lines to try to do the synchronization between the 6522 and the Arduino. And that worked most of the time, but it was never quite as rock solid reliable as I needed it to be. And I think the current version does a much better job of keeping both sides synchronized completely at all times. And I don't think that it really needs the interrupt. I think we should just be able to poll the state of CA2 here, the same way we're polling it up here at the beginning of read byte and write byte. And I don't know if this will make any significant difference in performance. There is this business here where we're resetting this signal received flag, and then there's an interrupt handler that will set signal received when there's a pulse on CA2, or when there's a positive edge on CA2, I should say. But this is just an assignment, and these functions here are not really actual function calls. These are just some macro nonsense that just end up calling some assembly language instructions for enabling and disabling interrupts. So I don't think it'll make a whole lot of difference, but I did want to try it and at least see what happens. And that just means we can comment out these 3 lines. And then here, instead of looking for that, we'll do something like what we're doing up top, but checking the other, checking if it goes low instead of high. Yeah, I think it'll be something like that. And I should do the same thing in write byte. And then we should just detach the interrupt. So I don't think this will make a big performance difference in and of itself, but if we don't have to have CA2 on a line that has to be able to receive inputs, then I have a little bit more flexibility for rewiring how the parallel port is hooked up to the Arduino, and that might let me make some of this business a little bit more straightforward. It might also mean that the actual serial port read-write lines into the Arduino were available again, which would be very convenient if I had a second USB to serial connection that I could hook up to it, which I don't at the moment, but we could get one of those. But for now, we're just going to flash the chip and update the board, and we'll see if this stuff still works now that we've made that change. Okay, and we have to reset the computer. All right, let's see if we've broken things or not. It still works. It's still much, much faster than it used to be. Oh, hey. I think we were at 0.38 before. I should have actually written those down first. I'll have to undo this change so I can add some data to my scorecard here. Let's see about the read also. Okay, well, assuming everything is still working and is still reliable, we have broken the 10x performance barrier. Nice. Let's do it one more time just to make sure. And just list a file and just see if this all looks correct. Boy, it sure does. I think now it's actually taking me longer for the serial port code to write that out to the console than it is to read the file off the SD card. Awesome. Although now I have to make sometime in the future to work on the serial port interface. Okay, so I've gone back and forth and I've collected some statistics for just the buffered I/O change and then again with the interrupt changes that we just did. So we can see what each of those contribute. And I'm still surprised that this one made a actually significant difference, but I'm not going to complain. I think the next thing we need to do is take a look at it in the logic analyzer. Boy, and I really don't need to capture for 10 seconds anymore, do I? There we go. Boy, that 1.31 seconds where we're initializing that buffer really stands out at this point. It's interesting that that part takes so much longer than actually transmitting the buffer across the parallel port and writing it to the SD card. I think that's a good sign of success, honestly. If we zoom in here where we're actually reading the program into memory, we can see that it's still taking us considerably longer to send stuff across the parallel port than it does to send it from the Arduino to the SD card, but the Arduino is faster than the 6502 and it's got hardware support for SPI, so it's not entirely a fair comparison. I think I'm pretty happy with where we're at right now. If we zoom in really far, yeah, before we were spending a long time waiting for the Arduino, and that is no longer the case. In fact, the whole time that we're doing this transfer of data is only about 10 microseconds. At least most of the time. If we zoom out a little bit, yeah, we can see every 32 bytes there's a longer gap, and that's where our buffered I/O is actually making a call to the SD library read function, filling up its buffer with 32 bytes of data. So that makes pretty good sense. I suppose we could make the buffer larger, but we're probably at a point of diminishing returns at this point. And I think I've set out with the goals I'd kind of set for myself. Let's see what our final values are here in terms of speed up. So let's see. For writing, we started out at about 2.73 seconds and finished at 0.3, let's call it 0.32 on average. So we're 8.5 times faster than we started out at. And then for the read test, which was the one I was more concerned about in the first place, we went from about 3.52 to, let's call that 0.3. 11.7 times faster than we were before. That's like a 1,073% speed up. Yeah, that'll keep me pretty happy. And you can see here when I do an ls command how comparatively snappy it is compared to how it used to be. Okay, I think that about wraps things up for this project, or this stage of the project. There's probably a few more things I can do, but I think we're getting much, much closer to the maximum that I'm going to get out of this parallel port implementation. I have some other pretty big plans for where I want to go with the Project 65 computer next, so we'll see where that goes and maybe revisit this particular element in the future. Thanks for watching.